So guys, listen, good job yesterday with that activity. I already put the grade in for that and the extra credit that you got if you had the whatever. We're finishing up the unit, or this half of the unit. 2.7 is our last section today, Monday, and that, I think I told you, once we finish 2.7, that's half of the material for this course. So we have the second half of Unit 2, and then Unit 3, okay? So we're about almost halfway in the new material, which is kind of crazy. This is very algebra-based. Some of it's going to be really familiar from Algebra 2. And then Tuesday, Wednesday is your test review. Thursday, Friday is your test. The test review, I'm almost done with it. If I can make it to the copier and the copier is working for once, I should have the review ready for you on Monday if you want it early. Okay, but it's for sure I'll have it on Tuesday for you. Okay. All right, let's get started. Composition of functions is taking one function and inputting it into another. It's like mixing two up together, following some rules, of course. And where that comes from is, here's a great real-world example of that. Suppose you want to calculate the cost to air condition your Florida home on a particular summer day. The cost for the cool air will depend on the average daily temperature, and the temperature will depend on the day of the year, right? So depending on how hot it is outside, your air conditioning bill, your electric bill could go higher or lower. And then depending on the day of the year, the temperature outside could be higher or lower. So the cost that you pay depends on two things. How much air conditioning you use, which depends on the time of the year, right? So it's like two things in one. And that's called composition of functions, putting one inside the other. And there's some notation we need to know for that. Okay. There's some notation, and it's right here. If you just want to zero in on this, these mean the same thing. We say it, that fog, it's f of g of x, f of g of x. Two different ways of writing the same thing. That little open circle means composition of g into f, but don't worry about it. The way we say it out loud is f of g of x, f of g of x, okay? The domain, this next sentence is confusing. The domain of f of g is the set of all x in the domain of g such that g of x is in the domain of f. Whenever they make those sentences, it just scrambles my brain. I have a really hard time understanding that. Let me put it into English for you. Same with this picture. This picture, maybe some of you look at that and it's crystal clear. I have the hardest time with something like that. I don't understand what they're saying. It's really, really simple. It's basically that when we talk about the domain of a function, we start with all real numbers, right? And then we take away anything that causes a problem in the function, okay? So restrictions, oh yeah, those are types of them. They come from really two places that we know of in this class right now. There's two situations where we are going to say it's not all real numbers. Like, for example, a line, a linear function, the domain is all real numbers. There's no restriction on the domain. And a parabola, x squared, a quadratic, the domain is all real numbers. There's no restriction on the domain. Exponential functions, we've been working on those. All real numbers. There's no restriction. There's two times there is. And you guys know them as having a variable in your denominator, right? That right away tells me x can't be 0. So if there's a variable in a denominator, these are the rational functions. That's when we learned about wholes and VAs. That was coming from our denominator. Anytime there was an x in the denominator, we had to say what x couldn't be because the denominator was not allowed to be 0. There's one other time where we have a restriction on the domain. Does anybody know what other type of function would prevent us from saying all real numbers? Wholes and asymptotes come from right here, the denominator. When there's a variable in the denominator on a graph, it looks like a whole or a VA. You're right. But the other time is a radical with an even number root. X has to be what type of number here? Or what can't it be? A negative. Right, William. It can't be a negative. X has to be greater than or equal to 0. Why equal to? Because the square root of 0 is valid. The square root of 0 is 0. That's okay. And any number greater than 0. Okay? We just can't have negative numbers under a square root, a fourth root, a sixth root, any even root. These are the only times we're going to have a problem. Okay? And so what they're saying in this crazy like sentence here in this picture is that when you plug something into another equation, no matter what your final answer is, your domain restrictions have to include what you plugged in. And I will explain that so much better with an example on the next page, but I'll come back to this concept in this sentence, okay? It's just much easier if I have a example to work on with you. All right, so let's do one composition of a function and just reintroduce to you guys what the commutative property is. The commutative property says the left side equals the right side. These two things equal each other. So if I know this, I know this, okay? So what the question is, if I find f of g of x, and then I find g of f of x, and I know I haven't done one of those yet with you, I'm going to here in a moment, can I determine whether the composition of the functions, what those two are commutative? Meaning, this is asking, is f of g of x equal to g of f of x? Are they commutative? If the answer is yes, they equal each other, then that's commutative. If they don't equal each other, they're not. So this is an important concept I'll come back to. Let's go ahead and do the composition of functions. So starting with f of g of x. Okay, so I read it left to right, f of g of x. But the way I work with it is right to left. We always start all the way to the right and plug in to the left. So I'm going to take my g of x function, I'm going to scoop it up and plop it right into the f of x function. Guys, in algebra, where do we plug stuff in? Like if I'm going to plug something into f of x, where am I plugging it into? X, right? There's only one place to plug it in. So what I'm doing here is I'm going to take g of x and plug it in to f of x wherever I have an x. And there could be more than one x. In this case, there's only one.
It's going to be 3 4 minus x.
So 3, yes. And then I'm going to put in my g of x, which is 4 minus x. So that's where x used to be, minus 5, right? So this is this function, just with x taken out and that plugged in. And then we simplify it. So distribute, combine like terms. And you could write this as 7 minus 3x or negative 3x plus 7. We're not real picky about being in standard form, but you do want to at least combine like terms, okay? So f of g of x is this, or negative 3x plus 7, okay? Let's go the other way. Let's do g of f of x. So I'm going to take f of x and plug it into g of x. So I'm going to take all of this and plug it into the other equation for x. No, that's a 4. 4 minus, and why am I adding in parentheses here? Well, because 4 minus x, x is a monomial. There's no parentheses there. Why am I putting them here now? Because what I'm plugging in is a binomial. That minus gets applied to the entire x, okay, which is 3x minus 5. So just be careful with your signs. This is like that nitpicky algebra stuff that we can't forget. A lot of people would have left that negative because they forget that the negative here goes to both, okay, and we get 9 minus 3x or negative 3x plus 9. Are these the same thing? Are they the same thing? No, not at all. No, they have to be, if you're going to put an equal sign in between them, they have to be the same. So the f of g of x and g of f of x are not commutative, okay? You're not going to get this question again. We're just proving here a misconception most students have, which is that f of g of x is the same as g of f of x. We just proved that the order that we input gives you a different answer most of the time. Mm-hmm. Yeah, it's just combining like terms. You only do the opposite if you're crossing over the equal sign. Yep, so I just did 4 plus 5. Okay? Good. Any other questions before we go on? So the next example, this is where that domain stuff is going to come in, right? There's 4 here. We're not doing D. We're going to do A, B, and C. A is the hardest, so I'm going to save it for last. Okay, so let's start with B. What we're given is 3 functions, f of x, g of x, h of x, okay? And then just different possibilities of composition. Okay, so starting with B, I'm going to take So I would read it as g of f of x, but I solve it this way. F of x gets plugged in to g of x. Okay? So find my f of x. Here it is. It's a quadratic, and I'm plugging it into g of x. So what I want to go back to is that domain thing. In the end, we're going to have to state the domain of our final answer. But what I want you guys to think of is whatever the restriction on f of x is, even if it doesn't look like that in the final answer, because things can cancel out. Like we might get rid of an x in the denominator or a radical. Before we even simplify this, I haven't even written it yet, I have to know that my final answer will always include my inputs domain. So if there's any restriction on f of x, it has to be reflected in my final answer. Now, in this example, f of x is a quadratic. There's no restriction. This is perfectly great, so you can plug any x value in. X to the second power, quadratic, no domain restriction. So we don't actually have to worry about it on this problem. Okay, so I'm going to take f of x and plug it into g of x. And I'm going to plug it in right here, right? So I'm going to have 1 over x squared minus 3x plus 2. Okay, so where I have red, that was an x. I took it out and plugged in f of x. And really, there's nothing else to do as far as simplifying. That is f of x plugged into g of x. There's no like terms to combine. But to be able to state the domain, I need to know, because I know there's a problem here, right? If I have x's in my denominator, there is a restriction on my domain. How do I tell what those restrictions are? Well, I need to factor this. I told you factoring never goes away in this class. It pops up all the time. The two numbers that multiply to get 2 and add to get 3 are -1 and -2. So by putting it in that form, I could easily see that x can't be 1 or what? 2, right? And I'm going to write it in interval notation. It's been a while, right? Remember, negative infinity up to the smallest number. And you can put union or comma, it doesn't matter, 1 to 2, and then 2 to infinity. That's how we exclude the 1 and the 2 in interval notation. Okay? Okay, let's do C. H of x into f of x. So I'm going to take h of x. Oh, this one has a restriction, right? It's got a radical in it. I know that x has to be greater than or equal to 0 on this. So I just want to kind of remember that when I have my final answer. Because sometimes the radical goes away when we do all the combining of terms and stuff. So if that happens, I still would have to say in my final answer that x has to be greater than or equal to 0. Because if not, we would never have been able to keep going. It would have been undefined. All right, and then I'm going to go into my f function here and here. There's two x's and plug h of x in there. So I'm taking that and I'm putting it there. I'm really making a mess with my paper. And there. Okay? So that would be the square root of x squared minus 3 times the square root of x. Right? So in place of this purple is where there was an x, and that's where I put in h of x. And now the simplifying. Remember, when you square a square root, they kind of undo, not kind of, they do undo each other. And just multiplying this times that would just be that. That's as far as we can go. That's our final answer. There's no restriction on this x, right? X can be anything. Remember, right before it, though, there was a restriction before we squared it, but there's nothing there. But we're taking care of that original domain restriction because it's in our final answer. So let me explain what I'm trying to get at here. Pretend that f of x was just x squared, okay? So if f of x was just x squared, and I plugged in the square root of x there and squared it, my final answer would be x, right? Pretend. That, if I just say, what's the domain of an x? You would say it's all real numbers. There's nothing wrong with that x. I can put anything in it. But before it was this x, it did have a restriction. So if this was the problem, we would still have to say x has to be greater than or equal to 0. we could not put a negative number here because we can't disrespect what it started as, which was h of x that had that restriction. But that didn't happen because there still is a square root of x in the final answer, so we probably wouldn't get this one wrong anyway, okay? So that would be from, that's a bracket. We're including the 0 to infinity. So from 0 to infinity is our domain. No negatives. Right? Last one, this is where I waited the longest. This has got some fancy algebra in it. G of x into f of x. Okay, I've made a big mess of this. But here's g of x, and I'm going to plug it in the same places as I plugged in the last one. Okay? So I'm going to plug g of x into that. So that's in parentheses, squared. Oh my gosh, my phone is going insane. 1 over x plus 2. Okay, and then minus 3 times that fraction. Okay, so I just plugged 1 over x plus 2 in for x and x.
Yeah, I see why you did it.
Yeah. Okay, so when you square a fraction, you square the numerator and the denominator. So I do 1 squared, I get 1. And we might have to FOIL this out, but let me just give you a hint. You can always do that if you need to. Sometimes it's not necessary. And in this problem, it's not necessary. You'd actually be doing more work than you needed to. So, it's hard for me to say when do you and when don't you, because the one I'm going to do in your homework, you do have to square it. But here's what I'm seeing as I move forward. I have a very similar denominator in this fraction I'm about to make. Let me show you. So this is like multiplying negative 3 over 1 times 1 over x plus 2. So I have minus 3 over x plus 2. What we're about to do is get a common denominator. We have to keep going with this. This is not done. We need to actually subtract these two fractions. To subtract fractions, you need a common denominator. Do you guys agree that my common denominator would be x plus 2 squared? So because this one's almost that, I can just multiply this guy by x plus 2, multiply the numerator, and then I have common denominators. If I had squared that out, I'd have a trinomial. So sometimes it's helpful to kind of look ahead, okay? So what I'm getting at is my first fraction stays exactly the same. I'm not changing that at all. And then on this bottom fraction, I'm multiplying let me fit it in here. I'm multiplying the bottom by x plus 2, right? That will give me x plus 2 squared. But don't forget, whatever you do to the denominator, you have to do to the numerator. I'm sorry, this is messy. Okay, don't forget, I'm multiplying a negative 3 times x plus 2. Go down here. So let me just write that because it looks so messy. X plus 2 squared minus 3x minus 6 over x plus 2 squared. Okay, so that's what this was right here. One last thing we can do is put them together. That was the whole reason we found a common denominator. There's my common denominator. And there was a few steps in here you could have skipped if you see. And then I have negative 3x. What comes next? Minus 5. That is your final answer. Or negative 5 minus 3x. It doesn't matter. That is your final answer. Now, just to make it one little step more complicated, that's fine. This is a good answer. I've also seen where when two factors have a negative, they'll factor out that negative. Okay, I would accept either answer, but just understand on a multiple choice test, you might have stopped here and your choice isn't there. You think, oh my gosh, something's wrong. Well, this does equal this. It's like GCF is the negative, so I've seen where they take it out, but it's not required. What can x not be, guys? No, x can be 0. Just negative 2. It could be 1. What would make my denominator 0? Negative 2. X can't be negative 2. So the way we write, do you see that, Jacob? Are you sure? Because I'm trying to think of where you got the 1 from. Oh, you have no. So that's how we would write it in interval notation, right? From negative infinity to infinity, skipping over negative 2, basically. Okay, so that one's a little yuck, right? Well, I mean, I'm hoping you don't have to show every step. Like, I probably would have gone right from this to this, but, you know, it just depends on where you are with it. So if you could write as many steps or quite a few fewer steps. Okay, we've done the hardest part of the notes in the homework. That's all we need the calculator for. We don't need a calculator for any of the rest of it, okay? This is just basically understanding. These are so easy. I feel like they're freebies. And I'm saying that because at first people are confused. And then all of a sudden it's like a light bulb moment. They're like, oh, that's all she's asking us for? This is exactly what we were just doing, but not with algebraically written functions, with graphs. But it's the same idea. Input is x, output is y, right? So what we're saying here, so look what we have. We have two graphs. One is labeled f, one is labeled g. That's important to notice the difference. Our first problem is starting to the right, going to left. Same idea, right? F of g of 3. So we're going to take g of 3 and plug it into f. What variable would you call this 3? What variable is that? X, right? G of x. This is just x. Watch, watch, watch. Go to my g graph. Here it is. Go to x is 3. Here it is. What is, if my input is 3, what is my output? Meaning when x is 3, what is y? 1. So g of 3 is 1. You guys agree? G of 3 is 1. So now we take the output from this, which is 1, and make it our input here. So we're going to do f of 1. So again, g of 3 was 1. Now I'm going to go to the f graph and find f of 1. Remember, this is still x. So f of 1 is 2. 2 is your final answer. Let's do another one. Takes a couple for it to click. G of 1, bless you, into f. Starting at my g graph, go to the x-axis. My x value is 1. What is my y value? 3. Let's make it even simpler. G of 1 is 3. Now find f of 3. Go to my f graph. X-axis is, here's 3. What's the y value? 2. Don't overthink. This is a coincidence that they're both 2. Okay? That's not what is going to happen. Look at this one. Oh my gosh, all these parentheses. What are she doing to us? Starting here, going here. Then we'll do this one. And then we'll take those two numbers and multiply them together. So it's just like 3 problems in one. Bonus. G of 4 is what? Nope. 0. Right? Do you see it, Levi? Dylan, why aren't you writing this down? And then on the f graph, f of 0 is 4. So that one equals 4. Maddie, are you seeing it? This one we're starting with f of 1. So we're starting at the f graph. We're always going to the x-axis. That number in the little parentheses is your x value. So f of 1 is right here. Find the output. So when f is 1, when x is 1, y is 2. What's g of 2? Okay, go to the g graph. X is 2. Y is also 2. And 4 times 2 is 8. Are we getting those? Kind of?
Not point at the light bulb.
All right, let's do another one. F of negative 1. That's just f of negative 1. So when x is negative 1, what is y? 6. My numerator is 6. That wasn't even composition of function. That's just what is x when y, what is y when x is negative 1. This one we have to do the two-stepper. G of 3, whatever we get, go to the f graph. So g of 3 is 1. F of 1 is 2. And we get 3. Did it just click?
Yeah.
It really happens like that for people. They're like, oh, I'm going to go on from here. If you did try these or want to, the answer for both of them are 4. Coincidence. But we'll practice more in the homework if you need more help, just so we don't spend all our time on those. Because really, if you're not getting that, you just need me to explain it to you one-on-one maybe, and you'll be like, it's so easy. All right, last two examples, more no calculator. It's really just understanding. There was a trend in cooking for a while where you would decompose a chef salad or like a Caesar salad. So instead of it like all mixed together, it's decomposing. It was taking all the parts and separating it. Decomposed shepherd's pie, where you had like a potato and you had the meat. So that was like a trend for a while. That's exactly what we're doing here. We're doing the opposite of composing. We're decomposing. You're going to take a function and split it into two. So it's like reversing what we just did. This is talking about inside and outside. So what we're trying to do is say h of x is f of g of x. So there's a g of x that's on the inside of f of x. So the way this is worded, g of x would be on the inside of f of x, okay, with that notation. It's what your g of x is what you're plugging in. Inside is what you're plugging in first to the last step, which in this case is f of x. I look at this and I go, wait a second. The best way to explain this, and she doesn't do that in her notes, but this is how I explain it. The outside one is kind of like your parent function. Okay? Just looking at this, algebra people, this is a quadratic, right? A parabola, moved left 3 places. What's the parent function of x plus 3 to the second? What are all the starting points, the most basic graph of this? X squared, right? That's your outside one. What did we plug in for x? X plus 3. Check it in reverse. If I plug x plus 3 into here, do I get this? Yeah. X plus 3 in for x would be this. What's the parent function for this one? It's one that we've done in this class. What's the basic graph? This is a rational function with all my points moved to the right 5. What points got moved to the right 5? 1 over x. That's the parent function for a rational function. The curvies in two opposite quadrants. This is where we introduce, like we have a VA and x equals 5 here. What did we plug in for x? X minus 5. Check it in reverse. X minus 5 gets plugged in for x. Yep, you get that. What's the parent function here? Square root of x, right? That's the most basic graph. Then we move all the points left too. So what did we plug in for x? X plus 2. Plug it in right there. You get that. This one's almost clearer to see. Now remember, I said I think of it as a parent function. I mean, if you have a squared in here, the parent function is x squared. Okay, so don't go that far with it. But look, you can see what got plugged in for x's. They're the same thing. So this is our outside function, right? What got plugged in for each of the x's? X minus 2. These should be really easy to check in reverse. You should be able to look at them and say, if I plug the inside into the outside, do I get the h of x? And you should. This goes into these and then gets h of x. Get some things rough, yeah. Okay. And last, finally. This is kind of like that air conditioning problem I told you, how one thing depends on another to get another something. And so listen to this word problem. And last period, I think we were confused a little bit because we're not farmers. So let me explain what it's saying. Jim plants wheat on his farm in Kansas, okay? The function W of A is the amount of wheat in bushels. Okay, bushels is like, whatever, boxes of wheat. I don't know, whatever. It's a measurement of wheat, okay? That he expects to harvest if he plants wheat on A acres of land. So W is bushels of wheat in accordance to the number of acres planted, right? So that's what WA means. Well, you don't have to write that. I'm trying to sum it up for you, okay? So, you know, every word problem we get, it's like H of T, the height of the ball after T number of bounces and time seconds, or I don't know, whatever it is. Okay, but keep going. When the wheat is harvested, so he goes out there and he gets it out of the field, he can calculate the amount of money, M, money, that he'll earn from selling W bushels of wheat. So W in both of them is the same thing. So M of W is money for all of his bushels of wheat. Okay, so that might be confusing. Let's just go to an example. What is W of 5 equals 275? So this is this one, right? This is number of acres. 5 acres will get us what? What's WA? What's this? 275 bushels of wheat. Okay, written in a nice sentence if you're taking a test. Look at this one. This is just taking them single, not composition. M of 65. So 65 is bushels of wheat. 550 is what? Money, the dollars. Yes. So if he, what's the 65 again? Okay. 65 bushels of wheat gets him $550. It's just interpreting it. So A and B should be kind of a review of stuff we've done in the past, just being able to interpret what that means. Now, let's take it and put it all together. Start here, go here, gets us this. Okay? So W of 4. 4 acres of wheat in the end gets me $2,100. 4 acres, so for every 4 acres he harvests, it will end up getting him $2,100. Putting it all together. Okay? All right. Let's go to the homework. This first page is the only page you need a calculator on, so I'm hoping you just get that done in the class. So find your practice set 1, write that down, and I'm going to do number 2 with you. Oh, sorry. So I'm going to do number 2 right now. Okay? So you're writing it right on your, are you still writing that? Let me just write down number 2. There's 3 parts to it if you read the directions. That's just mean. Okay? So you're given f of x and g of x, and part A is to find f of g of x. Tyler, did you not finish writing that down? Did you finish writing the assignment down? Dylan, did you write the assignment down? Okay, now we're going to do number 2 together. Okay? All right, so starting with g of x, I'm going to plug into f of x. Now look, quadratic line, no domain restrictions. All of these are going to have a domain of all real numbers. Because nothing has, whether you plug it in or what your answer is, you're never going to get anything that has a domain restriction. So I'm going to take g of x and plug it in to f of x. So here comes some more of our algebra 1 kind of stuff. When you plug 2 minus x in here, we have to simplify that. Okay, you don't leave it like that. We have to square this. That's FOILing. So you can go off to the side and do 2 minus x times 2 minus x and FOIL it out. Or, remember, there is a shortcut. You remember it, I would use it. Square the first term, multiply the inside together, then double it. So 2 times negative x is negative 2x, times 2 is negative 4x, and then square negative x, we get x squared. Okay, so that is that, and then plus 1. If you don't remember how to do that, just go ahead and go off to the side and put it all together. When I combine like terms, let's go ahead and put it in standard form. And 4 plus 1, 4 plus 1. And the domain would be all real numbers. We can make it a little shortcut there. We don't have to write it in a little notation. I know you guys know what it is. Right? There's no domain restrictions on lines or quadratics. Okay, so f of x into g of x. All of that in right here. So I'm going to have 2 minus, take out that x, plug all of that in, so I'm going to need parentheses on that. We don't have to square this binomial, right? We just distribute the negative. And then just clean it up a little bit. 2 minus 1 is 1. So negative x squared plus 1 or 1 minus x squared, it wouldn't matter. But we still have no domain restrictions. Questions so far? C is f of x. You can plug right back into the same function. We're going to take f of x and put it back inside itself. So you're going to take x squared plus 1 and plug it in right there. I'm going to need parentheses for that. X squared plus 1 squared plus 1. Right, this was x. You can either go off to the side and FOIL it, or when I do x to the second, that's a power property. Multiply my powers. 4. Multiply x squared times 1 together and double it. X squared times 1 is x squared, times 2 is 2x squared, and then 1 squared. So that is that. Don't forget there's another plus 1 right here. And you can combine those two like terms. Domain is all. Okay. I only gave you one more of those to do, number 3. Number 3 has some fractioning stuff. Actually, I'm just going to do 3A with you guys because I got that question a lot today already. Okay. So number 3, you're going to take g of x and plug it into f of x. So I'm going to take out that x. So this is f of x, right? And I'm going to plug in 2 over x in place of that x. So g of x is 2 over x, f of x. Okay? So square the numerator, square the denominator. And look, guys, if I wrote 2 as a fraction, it's like a 1, right? So this is, again, where we need a common denominator. What would our common denominator be? X squared, yeah. So this one's good. We don't need to do anything with that, but we're going to multiply this fraction. Whatever you do the denominator, you have to do the numerator. And then you can combine the numerators. That's just 4 minus 2x squared over their common denominator. And there's nothing else you can do with that. Now, this problem right here, my answer, what's just this answer? What can x not be? There's only one number x can't be, 0, right? 0. It can be a negative number, because if you square a negative number, it becomes positive. But don't forget, before we wrote it like this, there was a plug-in. So if, for example, if that had somehow resolved, we would still have to remember that x can't be 0, because that was the restriction on our input. But we're covered in this one, because x squared has the same domain restriction as x. X can't be 0. So your domain is from negative infinity to 0, not including it, 0 to infinity. Or you can shorthand write it, just x can't be 0. It doesn't matter. You're going to see this symbol. I don't know why she's using it all of a sudden. I've never seen it used in math. That means the domain is the element. Wait, what did I say? Sorry. The domain is an element of the set of all real numbers. This is when you see this, it means the same as this or negative infinity to infinity. She's getting all fancy putting this element symbol in there. Not necessary. So I didn't want you to be confused when you look at the key. Okay? So you see it right there. That just means X is an element of the number set of all real numbers. It's just all real numbers. Okay? So don't let that confuse you. All right. So I started 3 with you. Then finish 3. 5, 6, 7 is just one problem. And then you're done with the calculator. Dylan, can't sleep in here. Well, sit up is one of the first things you could do.